This discussion is on double integrals and area. So if we see the double integral over some region D of f of xy dA, f of xy corresponds to the height of something, and dA is the change in area. So height times area, summing all those up is going to give us a volume. So typically speaking, a double integral represents a volume. So let's visualize that. We see this picture, f of xy is this surface, and then we have the region D here, and we're looking for the solid that is under F above region D. Notice I picked a little piece of that region D. That's the change in area. We have the change in X times the change in Y times the height gives us the volume of this piece. So this Lego block is one piece. Change in X times change in Y times height. Length times width times height gives us volume. And then the double integral tells us to add all those up. So adding up all of the height times change in X times change in Y will equal volume. And our change in area there is change in X times change in Y. How do we see that? We saw that in that little rectangle that was there. Change in X times change in Y would be the change in area if we are decomposing our region into all of those rectangles. So then the question becomes, how could volume turn into area? How could volume turn into area? Well, there's something else for us to think about. If I have a prism, now what exactly is a prism? We have a height here that is constant, and every cross section is the same shape. Notice if I slice it this way, we're going to have a rectangle. Slice it this way, it's going to be a triangle. Slice it this way, it's going to be a circle. But the volume of those prisms and cylinders is just the area of the base times the height. So volume is area of the base times the height. So how can we turn volume into area? So keeping that in mind, volume is area of the base times the height. So how can we get volume to equal the area of the base? The answer to that is set the height equal to 1. So if I have volume equals area of the base times 1, then I get volume equals, at least number-wise, not necessarily in terms of units, but the volume is the area of the base. So if my goal is to determine the area of a region, it's simply going to be the double integral over that region of 1 times the change in area. And we need to think about how that change in area is going to work. So let's do a couple problems there. So we want R to be the region bounded above by y equals 9 minus x squared and bounded below by the x-axis. So let's visualize that. So here's our region, and we want to use a double integral to evaluate that area. So what is my southern boundary? That would be y equals 0. So using a double integral, southern boundary is y equals 0. And then what is our northern boundary? How high does that go? It goes up from y equals 0 up to this curve, which is y equals 9 minus x squared. So we go y equals 0 to y equals 9x squared on top. And then we have to, so we're going to go dy dx. And then we have to ask ourselves, how is x changing? So what's the smallest value of x I see in this region? What's the largest value of x I see? Smallest value is -3. And the largest value of x is +3. But then what did we say? We said volume is going to simply be the double integral of 1 dy dx. So this is what we get. Here's how we can do that. Dy dx, of course, is our change in area. So as always, we will start with our inner integral. which will be y goes from 0 to 9 minus x squared of 1 dy. The antiderivative of 1 is just y, and we get y goes from 0 to 9 minus x squared, which equals 9 minus x squared. So the area, which is my integral, simply will be the integral as x goes from -3 to 3 of my inner integral, 9 minus x squared. And you will notice right now that this is exactly what we would have done in one variable calculus to find the area under the curve, 9 minus x squared on the interval from -3 to 3. But quickly finishing this, what do we get? The antiderivative is 9x minus x cubed over 3, evaluated from -3 to 3, which will be 9 times 3 minus 3 cubed over 3, plugging 3 in first, minus plugging -3 in, 9 times -3 minus -3 cubed over 3. So 27 minus 9 minus -27 minus -9, and that equals 36. But the key thing to remember is that the area here is the double integral of 1 over that region of interest. That's our key idea. We certainly could have done this using Calc 1 strategies. But now let's take a look at a slightly different sort of question. So the question I want to ask next is, what is dA in polar coordinates? So let's compare the notion of polar versus rectangular coordinates so that we can discuss how the change in area is going to be affected. If this is my decomposition in rectangular coordinates, the change in area is this piece, change in x, that distance, times this piece, change in y. So we know in rectangular coordinates, dA is just change in x times change in y, or change in dy times dx. And we need to go ahead and think about how that is going to work in the world of polar coordinates. So here is our decomposition of a plane using polar ideas. So what do we have here? We have this distance times this distance to somehow approximate that change in area. So how do we figure that out? We need to do some geometry. So focusing on this, we have change in theta moving from here to here. We have a little r here, and we have a big R here. So we need to determine what that area is going to be for that piece of the sector. So to do that, we have to convince ourselves of what the area of a sector is first. So let's do that. So here's a sector. I want to figure out how to determine the area of a sector. A sector is a fraction of an entire circle. What fraction would that be? Well, whatever that angle is in radians divided by 2 pi is the fraction of the entire circle. This could be 1/8 of a pizza, for example. So we take the angle, whatever angle we have, divided by 2 pi, that's the fraction of the circle we have, times the area of the entire circle. The area of the entire circle is pi times the radius squared. So you'll notice what happens here is the pi's divide out, and I get 1/2 radius squared times the angle. Let's just keep in mind that the angle has to be in radians, right? Angles in radians, since I'm dividing by 2 pi. So that's going to be important for us to know. 1/2 radius squared times the angle. So if we're looking at this, I have two sectors here. I have a large sector, and then I have a small sector, and I'm interested in the difference of the two sectors. So the large sector, what is my area? It's 1/2 radius squared times the angle. So that's 1/2 big R squared times the change in theta. And then we have the small sector. What is the small sector? That's 1/2 little r squared times the change in theta, because it's the same angle. So the difference, the change in the area, is the difference of the area of the large sector minus the area of the small sector. So that'll give me 1/2 big R squared, change in theta, minus 1/2 little r squared, change in theta. Doing some algebra here then, what is my change in area? Factoring out the 1/2 times the change in theta, then I get big R squared minus little r squared. Let's take it one more step. Change in theta, change in alpha, change in A, change in area, I mean to say, is 1/2 change in theta. Now, big R squared minus little r squared is big R plus little r times big R minus little r. Okay. So how do we use that? What's my strategy going to be here? How do I use that? Well, what are we going to say? We're going to say that big R plus little r divided by 2 is average R. We see that? So here would average R be, the average of my two R's. Big R plus little r divided by 2 is the average of the R's. So big R plus little r is just twice the average R. Okay? So now I can make that substitution. Where is that going to put me? Change in A is 1/2 change in theta. Big R plus little r is twice average R times big R minus little r. Well, the 2's go away, and the change in A is R, average R, times big R minus little r, times the change in theta. But what is big R minus little r? Big R minus little r would be the change in R. So what I get then is I get the change in A is the average of the R's times the change in R times the change in theta. And we know everything shrinks to 0 as we go from deltas to d's. So when I get my differential, here's my big fact. dA is going to equal R dr d theta. dA is going to equal R dr d theta. So now we want to use a double integral to find the area of the polar graph. R equals 4 cosine theta. Let's remind ourselves that area is the double integral of 1 dA, and in polar coordinates, we know that dA is R dr d theta. So this is what we're working with. A is the double integral of 1 R dr d theta. Now, what does R range from? Where does R start? Where does R end? Let's discuss that. So starting at R equals 0, and then it goes out until it hits the curve, which is 4 cos theta. So R starts at 0, and R goes out to 4 cos theta. R goes from 0 to 4 cos theta of 1 R dr d theta. Now, what theta do I need to trace that entire graph? Let's take a look. Theta for that is from where to where. Notice if I go from 0 to pi over 2, not quite the entire graph, but if I go 0 to pi, I get the entire graph. So indeed, theta goes from 0 to pi. So this is what we want to solve, so let's go ahead and do that calculus. The first thing we'll do is evaluate the inner integral. The integral of R dr would be R squared over 2. Evaluated from 0, R equals 0 to R equals 4 cos theta. So that my inner integral is 4 cos theta squared over 2 minus 0 squared over 2. 16 cos squared over 2, or 8 cos squared theta. And now we're going to go ahead and find our integral. The area will be the integral, which is the integral as theta goes from 0 to pi of 8 cos squared theta d theta. And that's one of our favorite integrals, so let's quickly do that. The key to integral of cos squared or integral of sine squared is to start with this identity. Cos 2 theta is cos squared theta minus sine squared theta. Then using the Pythagorean identity, sine squared theta is 1 minus cos squared theta. We get that. Now we're at cos 2 theta is 2 cos squared theta minus 1. 1 plus cos 2 theta is 2 cos squared theta. And 1 plus cos 2 theta over 2 equals cos squared theta. That's the substitution we're going to use. So we have the area is 8 times 1 plus cos 2 theta over 2 d theta. Pull the 4 out in front. 4 times the integral as theta goes from 0 to pi of 1 plus cos 2 theta d theta. Let's finish that integral. The integral of 1 is theta. Integral of cos 2 theta is sine 2 theta over 2. You need to do a u substitution to get there. And let's go ahead and finish this. Plugging in those values, I get pi plus sine 2 pi over 2 minus 0 plus sine 0 over 2, which is 4 times pi plus 0 minus 0 plus 0. After all is said and done, the answer to that is 4 pi. Now, is that what I expected it to be? Here is my curve. It has a radius of 2, the area of a circle with a radius 2, pi r squared, pi times 2 squared, 4 pi. So indeed, that is correct.